All right, so today we're going to continue our discussion on representations. We saw fusion on Tuesday. Today we're going to continue talking about coordination and fission. So recall representation is the first challenge we're going to talk about in multimodal. The whole idea is that if you have two elements from different modalities, we call them usually local features. So I'm ignoring the structure of other elements in the modalities. I'm just focusing on, for example, one word and one object region. There's three ways to learn representations, right? The first way is to combine these two elements into one feature. That's called fusion. You're combining the information in order to learn what cross-modal interactions exist across my two modalities. We saw it on Tuesday, a lot of different methods for fusion. Today, we're going to look at coordination and fission. Coordination, the whole idea is to learn separate representations, one for each modality, but coordinate them using some similarity function. And we're going to see how that is useful. And finally, in fission, we're going to look at learning more representations than we started with, perhaps take into account different clusters or different factors that might exist in my data. All right, so representation coordination. So again, the schematic is simple, right? Two elements learning two separate representations that are coordinated in the sense that they share some similarity, and we're going to look at different ways of enforcing this similarity between these two representations. That can be a spectrum from strong coordination. We're really enforcing this similarity by a lot. On a spectrum to more partial coordination, we're only enforcing a similarity very little or perhaps only in some dimensions of these two representations. So a lot of work in coordination is going to look at different ways of designing this similarity function and learning this similarity function to get either a spectrum from strong to partial coordination. So perhaps when I say similarity, a general way of learning these models is that you take each modality, your elements, pass them through some encoders, f of a for your first modality, f of b for your second modality, to get features, and define some coordination function. Usually this coordination function measures some amount of similarity between your representations. Following that, a general learning paradigm is to pass your elements through your encoders, f of a, f of b, get representations, measure their similarity, and treat that as your loss function. So in this case, you want to maximize the similarity of pairs that are similar to each other as judged by you. And eventually, you're going to train it for some model parameters theta in f of a, your encoder for the first modality, your encoders for your second modality, theta f of b, and whatever parameters may exist also in the coordination function, g. So usually this involves some amount of paired data, right? Paired data, which you know should be similar. You want to exploit the fact that they are similar, that there's some connections between them. And one very simple example of learning a similarity function is cosine similarity, right? You want these two representations, ZA and ZB, to have a very high dot product, or in other words, are parallel in your representation space. And the norm of Z of A of Z of B is just to normalize it. So you're not getting arbitrarily high dot product just by having vectors of high magnitude. So you normalize them by their L2 norm. So cosine similarity is a very common example. I'm sure all of you have seen examples of cosine similarity, but that is one of the classic examples of coordinating representations. Learning image embedding, learning a text embedding for paired data, for example, images and captions, and coordinating them by making sure they have high cosine similarity between your representations. So that example is an example of a strong coordination, right? You're making sure that every dimension is coordinated. They're very, very similar in all the dimensions. Okay, so beyond cosine similarity, you can very easily think of other examples of similarity functions. For example, kernel similarity. So in fact, kernel is any function that measures similarity between ZA and ZB. A linear kernel recovers the dot product between ZA and ZB, and therefore recovers cosine similarity. But you can also go beyond, right? Polynomial, exponential, RBF kernels. And if you've taken any machine learning class, you know that kernel functions measure similarity across data points in some representation space. And this representation space can be higher dimensional than a data points that came in from the data points. So for example, if your data clusters may not be separable in 2D space, they might be separable in 3D space, right? When you add a z-axis. So kernel similarities take advantage of this fact and define a similarity function, not necessarily in the same input space of your modalities, but perhaps some higher dimensional space. For example, this RBF kernel. So again, different ways of designing. As long as you have a good similarity metric between your modality representations, you can plug them in to coordinate representations. Another example of slightly weaker, or as I called it in the beginning, partial coordination is to use correlation. If I have two representations, ZA and ZB, and I have a population of them, can I make sure that they are correlated in your space? So correlation is a bit weaker because let's say these are my two representation spaces, X and Y, and I'm using the same color to represent paired data. So over here, yellow, you have data from, for example, images paired with embeddings for your captions in yellow. And for purple or red, that's another paired data with that side. So correlation-based metrics don't measure similarity on individual embeddings, like we saw for cosine similarity or kernel similarity. They measure similarity across the entire population, right? For this entire population of vectors from X, the correlation roughly points in this direction. For the entire population of representations in Y, my second modality, my correlation roughly points in that direction. Can I learn transformations, U and V, for my two embedding spaces X and Y, so that they are correlated in the same direction, right? So that's called correlation analysis. A slightly weaker form of similarity because, as I mentioned, the similarities are no longer measured at each pair level, but they're measured across the whole population, right? You have an entire correlation for all your image embeddings. You have entire correlation in the space of all your text embeddings. Can I learn a linear transformation so that they are maximally correlated in the same direction? Right. And recent work has also extended this for deep learning. You can take embeddings, pass them through many nonlinear layers to get representations. Likewise, for image embeddings, go through many nonlinear layers to get some representation. And again, given the whole population, I can compute the correlation in each of their representation spaces and try to maximize their correlation so that they're aligned. Okay, any questions about what I've said so far? We looked at a very simple example of similarity. This should be very natural. We've probably seen it before. Cosine similarity, kernel similarity. Probably the only thing that's new is probably this correlation, maximizing the correlation in your two representation spaces learned. Coordination imply partial coordination. Technically, yes, but instead of thinking of these as think of these as more ways of categorizing your methods. Sometimes you want to enforce coordination across every dimension and across all your paired samples. So you might choose a method like this. If you want to do, for example, really fine-grained image text retrieval or image text captioning, you might prefer something like strong coordination. Partial coordination makes more sense when you want to get some amount of alignment, but that is not your end task in itself. So for example, if you maximize the correlation in your representation spaces, you're not necessarily minimizing the distance between every single pair of image and caption. Right? So think of it more as different conceptual ways of choosing what form of similarity function you might think is most suitable. Okay, correlation. So one final example I want to mention, also in regards to similarity functions, is this work on learning a multi-view intact space. And so the hypothesis essentially is that there is some underlying space of all the concepts in the world. For example, animals, people, tables, objects, and so on. And different views or different modalities that we see in the world are simply transformations of this underlying latent space. And in particular, this transformation is not complete. It is in some sense degenerate. For example, if I have a human, I can see them, right? That's one view. The underlying concept is a human, it's a person, I can see them in one view. That's going to be a very impartial view because it ignores everything else, like what the person is saying and so on, what a person smells like and so on. Another view could be what a person is saying and so on. So essentially, you can also learn coordination by trying to recover this latent space that contains all the complete information about your concepts, given only the partial views that you observe in the world. The partial views are different modalities that you observe. So this method called autoencoder and autoencoder essentially assumes that there is some latent intact representation. This is the complete view of all the concepts that you might want to learn about. And every real-world manifestation of these views, for example, in text and images, are just partial representations of them. So in other words, I should be able to learn a transformation that takes my latent intact representation, that's an actual underlying concept that is complete, and transforms them into partial spaces. For example, text representation space or image representation space. So for example, these vectors G should be similar to your auto-encoded text vector that goes from text to text. And this representation G for image should be very similar to your image autoencoder representations. So essentially training two autoencoders on the text side, on the image side, to learn intermediate representations. And those intermediate representations should also be similar to this underlying latent representation. So again, an example of coordination, right? Because you're learning two separate representations, one for text and one for image. They're separate. I'm not fusing them, but these two representations are coordinated using some similarity. In this case, similarity is not defined as simply by cosine similarity, which doesn't have any parameters, but in this case, the coordination function has parameters in itself. The coordination function is essentially saying that I can transform one of my text embeddings to my image embeddings through this transformation network that is also learned end-to-end. So that's why they call it autoencoder in autoencoder, because you have autoencoders separately for each modality, text and image, to learn embeddings. And you also have an autoencoder that is used to define the similarity between my text embedding space and my image embedding space. Okay? So a slightly more complex version of defining similarities, where there are parameters to learn within a similarity function by itself. Yes?
Do we predefine H as a prior space, or do we learn H?
H is learned, but you can look at the paper for more details. I'm sure if you impose some priors, you just get the variational autoencoder version of autoencoder. But it's just so an example where the coordination function, or in this case, the similarity function, has parameters in itself. And finally, gated coordination, right? If I have two modalities, I want to learn a representation that's coordinated. Instead of having them that are static representations, they can also be gated representations. In other words, the representation changes for every single input. So over here, the function will look like ZA will be a gated function that depends on the modality itself and the other modality times XA. And the representation ZB will be a gated function of modality B itself and ZA times XB. So again, coordination, because you're learning two separate representations, but these two representations are gated because they depend on both the modality and also the other modality. So this might look a little bit familiar with gated fusion that we saw on Tuesday, right? But the main difference is that gated fusion, you're learning these gates to dynamically tell you how to fuse your modalities. Here we're learning the gates to dynamically tell you how to learn separate representations, ZA and ZB, that you can then subsequently coordinate using some similarity function. And again, this is related to attention modules, self-attention. We're going to talk about that. So to summarize, you've looked at a lot of examples of coordination. The whole idea is that you want to have two modalities learning two separate representations. These two separate representations should account for the fact that these two modalities have some underlying connections between them, some underlying similarity between them. So we went through a couple of examples of similarity functions, the simplest being cosine similarity. For people who came in late and missed the first half of the class, simplest being cosine similarity, dot product in representation space. That's a special case of a kernel similarity, where the kernel is linear. You can go to arbitrarily more complex kernels. Both of them are strong examples of coordination because they enforce coordination for every pair of points. Correlation is an example of a weaker type of correlation, weaker form of similarity, because correlation is defined over the entire population. All my image embeddings has a correlation. All my text embeddings has a correlation. I want to maximize that correlation. We also looked at examples where the similarity function has some trainable parameters within it. So cosine similarity, kernel similarity, that's just a distance function, doesn't have any parameters, but you can also learn a similarity metric with actual trainable parameters. So that was autoencoder and autoencoder. And finally, gated ways of coordination, where the embeddings themselves depend on both the modalities. All right, any questions so far? Any questions about these coordination functions? Yes, the intuition behind this multiplication. Right, so in this case, think of the gate as just weights. Normally, if I have XA, I'm going to pass it through some neural network, some weight function, but those weights are static, right? Those weights are always fixed. That means the same data is passing through the same weights to get your representation. Sometimes you want your data to pass through dynamically changing weights. So for certain data points that are more important to your task, you want it to learn a higher weight. For some data points that are not so useful to your task, or where the data is noisy, you want to learn a smaller weight. So you can think of these functions G as weights. They essentially tell you how much each modality should be contributing to your representations. And these representations can be used for fusion, as we saw last week. We saw gated fusion. So how much each of these should dynamically contribute to my fusion. The only difference here is that how much these modalities should dynamically contribute. So pretty simple. Different examples of similarity functions. So now that we've seen similarity functions, you recall that's the G function over here. How can we actually train all of these models? And as a general paradigm, contrastive learning, you've probably heard of it. But essentially, the idea is that you typically start with some paired data. This paired data represents data, for example, images and text descriptions, which have similarity between them, which you want to coordinate. So for example, you have paired data. Green shows your positive pairs. For example, positive images and the actual captions. And red shows the negative pairs. So that will be the same image, but with random captions that don't describe the image. So you're going to learn these models using a contrastive loss that brings these positive pairs together according to the similarity metric you've defined. And you want to push negative pairs far apart, again, based on a similarity metric you've defined. So it could look something like this, right? You want to maximize the similarity between ZA and ZB, positive, so we denote with a plus sign, and you want to minimize, so in other words, minus the similarity between ZA and ZB with a negative sign. Positive pairs and negative pairs. Right, so these similarity functions can be any thing I mentioned previously, simplest being cosine similarity, but also extends to all the other coordination functions. So this is a hinge loss version of contrastive learning, and soon after you see the more classification version of contrastive learning, but they're all similar in idea. So what it looks like in practice is that you can do some really cool things, right? If I've learned a representation space that is coordinated, in other words, I should be able to learn the fact that these images represent very closely in similarity space to the word embedding representing that image. So some simple things I can do is I can take an image of a blue car, embed it into representation space, subtract the embedding of blue, the word blue, plus the embedding of the word red, and given that embedding, retrieve nearest images in that space. And you actually get red cars. I can do it for school buses that are yellow in color, minus yellow plus red. You get fire trucks or buses that are red in color. I can take airplane image, embed it, minus the word embedding of flying, plus sailing, and retrieve the nearest images, you get sailboats. And finally, this really cool example, you take a cat sitting in a bowl, minus bowl plus box, and you get cat sitting in a box. So of course, this is only possible because you have learned a coordinated representation space that enables image to text retrieval based on the semantic meaning, right? You have images that have some semantic meaning of flying. They're actually very close to the word embedding for flying in that space. And finally, the second thing that makes all this possible is that there is some notion of compositionality happening. That is successfully decoupled the presence of cats in the image and the bowl in the image so that you can only change the bowl to box while keeping the cats. So two things that kind of make this possible. Now, of course, nowadays, I can't talk about coordination without talking about CLIP, right? CLIP is probably the largest scale demonstration of coordination in practice, but the idea is very similar. You again take positive pairs from the internet, so lots of images with lots of captions, and these captions go beyond the individual words or phrases we saw in the previous example to really longer captions, right? These can be obtained from Wikipedia, from Instagram, any place on the internet where you believe that there's natural descriptions of images. Pass your batch of images through your image encoder, pass your batch of captions through your text encoder. You get something that is batch size by batch size large matrix. Everything along the diagonal are the similarities representing positive pairs, right? Everything off the diagonal are similarities representing negative pairs. So one modified version of contrastive learning, instead of the hinge loss that you saw previously, but rather a division loss, can be given by getting a similarity on your positive pairs in the numerator. You want to maximize that, divided by the similarity of the negative pairs on the denominator. You want to minimize that. Technically, you want the division or the minimization to only be on the negative pairs, but most people in practice minimize both the negative and positive pairs because if your batch size is large enough, so in this case, n is your batch size, you have like one positive pair and n minus 1 negative pairs. So even kind of minimizing that positive pair doesn't really affect the loss too much when n is large. Here's a trick that people found to speed up your implementation and training tool. But same thing, the similarity function can be any of the similarity functions that you saw. Simplest case, cosine similarity. That's why every entry in this matrix is just dot product. Dot product cosine similarity. Okay. And these models are really powerful. These models, you can take the encoders, your text encoder, the image encoder, and use them for many zero-shot. You've seen the zero-shot vision tasks where you can take any other set of images. You can put any possible captions or any other categories that you want to classify your images into. And based on the similarities, you can retrieve the closest caption or the closest attribute or closest object. So in some cases, people call this zero-shot object categorization or object detection, because previously, if you train image models, you had a set of image and you had a set of predefined categories. You couldn't go beyond these categories, right? And now, given these images, you can put categories based on any natural language description that you want into your text encoder, and it's still going to be able to classify based on your cosine similarity, which of these text descriptions, anything that is text is passed through a text encoder. But these two are no longer in separate spaces, right? These two are, if you train them correctly, in one homogeneous space, where you can take blue car, image embedding, and it should be extremely close to the word embeddings of blue and car, or even like blue plus car or something. So that's why that's the result of you maximizing the similarity, using these coordinated representations to make sure that your image embedding and text embedding are really close. So they're all right. So let's go into a bit of more technical depth to try to explain why these methods work. And it shouldn't be hard to have an intuition that these methods work. These coordinated methods work because they're exploiting the information in both modalities. There is some underlying similarity given by their pairing. And by doing contrastive learning, you are capturing the information in both modalities. The fact that sometimes you have images, and you have text that describes the people, objects, and actions within the image, and so on. It may or may not come as intuitive to you that it will also discard any information in images that is not present in text, and any information in text that is not present in images. Right? So it's going to kind of discard the unique information. But exactly why, we're going to see a little bit. So one way of formalizing, one language of formalizing what we mean by information that is shared and all these concepts is through information theory. Information theory gives a precise mathematical definition of what information means and what information sharing between two data sources, or more generally random variables, means. So information theory is created by Shannon. The main intuition is that the information that some source gives me, some random variable gives me, depends on how random the content is. So there are two examples. X always giving me 1. Right? And another example, X, which is toggling pretty randomly between 0 and 1. The idea is that X here should give me more information because it is more random, whereas X that always gives me 1 gives me less information. So how can we formalize this? One way of formalizing is to say that the information content, roughly for every little x, for every element in the sample space of a random variable big X, the information is roughly proportional to 1 over the likelihood P of X of that element occurring. Specifically, the proportional sign means that it is roughly log of 1 over P of X. So over here, the probability of 1 happening is 1, right? You always see 1 happening. That's going to give you 1 over 1 bits of information, log that. Over here, you have X happening at probability 0.5, roughly, and 1 happening at probability 0.5. So the information that 0 gives you is roughly 1 over 0.5, roughly log 2 bits of information. And likewise, information that the bit 1 tells you is roughly 1 over 0.5, again, log 2 bits of information. So the key idea is that the more randomness there is in some distribution, the more information you can hope to gain from it. Whereas something that is just, in this case, not even a random variable, just a deterministic variable, has the least information. So that was the information content for one particular element in the sample space of X. In general, for the entire distribution, for the entire random variable, the information is given by the entropy, being the expected value of the amount of information content for every element. So basically the expectation over all x in your sample space, the information content, negative log p of x. So again, entropy can also be defined for continuous random variables, but essentially summarizes an expectation for all occurrences of random variables, of the elements in a random variable, how much information it gives me an expectation. So visually, people like to look at entropy like this, right? They draw these circles, and sometimes if these circles intersect, you get Venn diagrams. But essentially, the circle with the area telling you how much entropy there is. Smaller circles representing less information, lower entropy, and larger circles representing more information, higher entropy. All right, so usually you use these circles to define entropy of a random variable. So if these two circles don't intersect, then it means that these two random variables are independent. Right? I can compute entropy of A modality, entropy of B modality separately. But of course, in the real world, we know that most of these modalities share some connections. Right? There is some referential information in a text that explains some of the information or the visual occurrences of objects in the image. And we looked at all these different ways of why these connections can happen, right? Either associations or from more semantic perspective that they actually correspond to the same underlying object. So generally, we draw Venn diagrams like this. Right? We have two modalities, each containing some information. Again, the area, the total area in A represents the entropy of that modality, the total information in that modality. The whole area in B represents the entropy or the total information in that modality. And you also get three other areas. The first area is entropy of modality A, conditional modality B. You have entropy of B conditional on A. And finally, a thing in the middle, or before that, conditional entropy, the definition, is very similar to entropy, right? Just that instead of taking in the expectation log P of X, you're putting in the conditional distribution P of Y given X. And you're computing, again, for each of the elements Y in the sample space. After I condition on X, how much information do I get? An expectation over all X's and Y's in the sample space. So that's conditional entropy. Essentially saying that if I observe X, so normally you have P of Y, right? That's the distribution of Y. But now I'm observing X. Now I get a conditional distribution P of Y given X. I'm essentially asking, after observing X, how much of Y's information do I get explained? If X and Y are independent, then your P of Y given X essentially boils back down to P of Y. Conditioning on X doesn't tell you any information about Y. And therefore, your entropy of Y given X recovers entropy of Y, right? The total information of Y given X is just the same as if you just had Y by itself. X tells you nothing about Y. If X fully determines Y, on the other hand, for example, if X or Y are the exact same random variable, or even if the fact that Y is a deterministic function of X, then P of Y given X, any occurrence of X perfectly explains Y, right? Perfectly recovers Y. And therefore, your entropy of Y given X becomes 0. There is no more randomness. There's no more distribution. It becomes a deterministic outcome, what your P of Y given X is. So entropy of Y given X becomes 0. So you can also show that any conditioning on X within these two spectrums, within a spectrum independent, that doesn't reduce the conditional entropy of Y given X. If X fully determines Y, then it reduces to 0. But in general, any conditioning on X is going to reduce the entropy of Y given X smaller than entropy of Y. That's why typically in these Venn diagrams, the entropy area is going to be smaller than the total entropy of that modality. So that's conditional entropy. And finally, mutual information, right? So that's the information shared between both modalities, and mutual information gives us a very precise definition of that. Mutual information can be given by the total entropy of that modality, entropy of X, minus the entropy of X after conditioning on the other modality, entropy of X given Y. Again, you can write that down by definition of H of entropy of X and entropy of X given Y. You essentially end up with a pretty nice expression that basically says, I'm going to take the ratio of two things. Right, the numerator is my joint distribution, how much X and Y co-occur in their joint distribution. And I'm going to compare that to the denominator, which is a product of P of X marginal distribution and P of Y marginal distribution. So in other words, how different is my joint distribution when I have both X and Y versus just a product of X and Y's marginals as if they were independent. So any additional information that your joint distribution gives you, X and Y, as opposed to your two marginal distributions as if they were independent, contributes to the mutual information between X and Y. And again, it shouldn't be hard to see that if X and Y are independent, then P of XY joint distribution factorizes into P of X times P of Y. The numerator and denominator cancels out. The mutual. And another way that you might have seen people write mutual information is the KL distance between two distributions, one of which is the joint distribution between X and Y, and one of which is the product of marginal distributions, P of X times P of Y. And again, the KL divergence is just a way of formalizing how two distributions are far apart from each other. So again, if the joint distribution is very far apart from the product of marginals, it's high mutual information. These two modalities are very highly non-independent. Whereas the KL divergence is 0, then these two distributions become the same. You're essentially saying that X and Y are independent. So that gives us a language to formalize what we mean by information as entropy, as conditional entropy, as mutual information, and also a language to formalize what it means for there to be shared information between two modalities as using mutual information, and what it means for information to be unique in one modality not present in the other, as given by conditional entropy. Any questions so far? Entropy, conditional entropy. Sometimes we like to make the assumption, or some people like to make the assumption that if I have two modalities, the only thing I care about is the mutual information between them. So a lot of work in representation coordination is based on that assumption, that if you have images and captions that are paired together, the only thing that I care about in modeling is the fact that these two images and captions correspond to the same thing. I'm going to ignore everything else. So information, the assumption is that information present in both modalities is the most important for the downstream task. And in fact, we can prove, and I'll show the proof in a little bit, that these methods based on contrastive learning, the one that we saw earlier, these contrastive learning objectives that maximize the similarity of positive pairs and minimize the similarity of negative pairs, actually has a relationship with the mutual information between these two modalities. So in other words, you might have heard people say that CLIP or contrastive learning focuses on shared information or focuses on the mutual information. We're going to look at why people say that. So here's a very simple derivation, right? So again, I'm going to start with the info NC objective. That loss is the negative expectation of F for your positive pairs. So I'm rewriting, I'm writing F as a critic function. What this F basically represents is all the trainable parameters, right? Your element in the first modality pass through your encoder, element in the second modality pass through your encoder, and you take a dot product, cosine similarity, whatever. Or you can even have trainable parameters in your similarity function. All that branch from your data X, A, and XB to your final score or your similarity score, I'm going to write that as F, right? That's a critic function, typically called in the literature. And again, these coordination losses basically try to maximize the critic function score for positive pairs and minimize the critic function score for negative pairs. Right? Everything that we've seen before, here's a general way of writing that equation. So you can show that when this loss is trained to optimal, right, when this loss is trained to 0, then essentially what you're training the critic function to do is to be a binary classifier that is able to distinguish between positive pairs and negative pairs. Right? You want to maximize the similarity of positive pairs, you're going to minimize the similarity of negative pairs. Essentially what it must function as is a binary classifier that can actually figure out what are positive pairs, and I should assign high scores to it. And what are negative pairs, I should assign low scores to it. Okay? That's if it's trained to optimal. Of course, in practice, it may not be trained to optimal. And what positive pairs mean are essentially XA and XB sample from the joint distribution of A and B. Those are positive pairs. And what negative pairs actually means are XA and XB that is sample from the product of marginals. So I sample XA from P of A, I sample XB from P of B, assuming they were independent. That's actually what positive and negative pairs mean. Right? In practice, in your data set, what that means is that your joint distribution of A and B comes in your paired data. If I have 10 images and captions in the form of paired data, every row in those 10 are A, B sample from the positive distribution, from the joint distribution. What negative pairs means is that I take any of the 10 images, I randomly pair with any of the 10 captions, I get 100 of them eventually. That's a negative pairs, the product of marginals. Okay? So the critic function f must be trained to be a binary classifier that's able to distinguish between these two tuples, the joint versus product of marginals. And again, for the joint, assign high scores to it, high similarity. For these negative pairs and the marginals, assign low scores to it. So it's trained to be a binary classifier distinguishing that. Then you can show that an optimal loss, this classifier, f star, so you train it to completion. What it must do is it must basically estimate this ratio. The ratio for the current XA and XB that you give to it, the ratio of P of XA, XB, joint distribution, divided by the ratio of P of A times P of B, product of marginals. Right. We must estimate this ratio, and essentially the higher the numerator is over the denominator, the more likely that it is a positive pair from a joint distribution, and the critic assigns high scores to it. And the more this becomes close to 1, where XA and XB are negative pairs, so from the marginal distribution, the lower I assign the score to it. So optimal loss, the critic actually follows, is proportional to this ratio. And if you plug this optimal critic again back to your loss and rearrange, you actually obtain something that almost exactly resembles mutual information. Again, you have the expectation of log, is just the reverse of the mutual information times the n, where this n comes from a number of negative samples that you have. And that is essentially equal to the negative mutual information between A and B, because the ratio is reversed, plus log of n, where n is the number of negative samples that you have. That is, if you train these info NCE or contrastive learning objectives to optimal, your final loss looks like that. So rearranging, that gives you the mutual information between XA and XB is at least log n, where n is the number of negative samples, minus your loss at optimal. Right. So what that essentially means is that I'm training info NCE for that loss. Right? And if I treat kind of negative loss, well, there's a negative sign because you're minimizing your loss, but you can also think of negative loss as maximizing the objective. So essentially, when I do NC, I'm maximizing an objective that is a lower bound on my mutual information. On the lower bound, the gap is kind of given by a number of negative samples. So that's why when you hear people say info NCE or contrastive learning is capturing mutual information or learning shared information, precisely what it means is that your info NCE objective is maximizing or optimizing a lower bound on mutual information. Okay, so kind of that's where the precise connection between contrastive learning and mutual information comes from. So of course, the better you train your NCE, right? The better you train it, the better you can kind of maximize the lower bound of mutual information and eventually approach as much mutual information as there is in your data. Okay. Also means that if your XA and XB are independent, so your modalities don't have connections, right? Then your mutual information is 0. Then maximizing any lower bound of mutual information can only approach 0. That means contrastive learning will not be that useful. Okay? So the higher the mutual information between your modalities, the more space, the more opportunity you can to maximize the lower bound on your mutual information so that contrastive learning actually learns something. Any questions so far about this derivation or any of the intuitions behind contrastive learning? And so this is actually the original paper, CPC, not the clip paper or whatever recent heuristics they made to it. I'm sure if you had a temperature, you'll probably be some constants here and there, but it will not affect the main idea. Because as long as your critic, as long as these critic functions, and these critic functions are the ones that take in positive pairs, assign a high score, high similarity, take in negative pairs, assign a low similarity. Essentially, if you're distinguishing between positive and negative pairs, you're going to get a critic function that roughly estimates the ratio between your joint distribution and your product marginals. And then you can eventually get something that resembles mutual information. Learning, coordination, they learn the mutual information, right? What if what I want for my task is not within this mutual information? Right? Then you might be in trouble. And these folks actually did show that you might be in trouble. Normally, if your task is exactly in this mutual information area, the information required for your downstream task, then contrastive learning or all these objectives are going to do really well, right? Essentially, they're learning just the right amount of information, nothing more, nothing less for the task. And you can formalize that by saying that the mutual information between your two modalities, X1, X2, is roughly similar to the information between your modality, X1, and your task Y, right? So essentially saying that the area that is shared between the two modalities is similar to the area that is required for your task Y. Of course, that is a pretty strong assumption. You can also have cases where you don't have enough signal, right? The amount of information that is shared between your two modalities is less than the information that is required for your task. So that's too little information. You could have settings where you have too much information, that your information overlap much more than the information actually required for the task. So if you do that, then contrastive learning or your coordination learning is going to learn much more information than required for the task. A lot of that information is going to be unnecessary. So in practice, they showed this plot where on the x-axis is the information between x1 and x2 from 0 all the way to a large amount. When it's 0, essentially this area, your modalities are independent, right? That means there's not any shared information between them. Doing contrastive learning is not going to get enough information required for your task. You're going to eventually increase the amount of overlap between your modalities until a sweet spot. And this sweet spot is exactly when your overlap is equal to the information required for a downstream task. And at that point, you're good, right? You learn the right amount of information. And of course, if you further increase the connections between your modalities, you're learning too much shared information that's irrelevant for your task. And you can see here over in performance, right? When the connections are very small, not doing very well in performance, you see performance gains gradually as the amount of overlap between modalities is increased up until the sweet spot. That's this peak over here. And finally, if you increase the amount of connections or shared information beyond that, you're going to have too much noise and the performance drops. Right? So a very cool example of how contrastive learning is great, but it has this underlying assumption that you're operating when a task relevant information is roughly perfectly within the overlap of your two modalities. Give a mutual information. So this one, a precise definition is how much mutual information there is between my two modalities. That's going to give me a number in bits, an actual number you can compute. And they're actually comparing it with how much information lies between your modality and the task. Again, by mutual information, right? You can X1 and Y. You can, again, compute that exactly. Well, not exactly, but okay. Yeah, good question. So these folks, they study in the context of multi-view learning, not exactly multimodal learning. So in multimodal, you typically assume image and text, and the modalities are given and fixed, right? And there is a mutual information between image and text. Another branch that is very closely related is multi-view learning, where you start off with one modality, say image plus image. So image is X1, and Y is your image classification task. And V1 and V2 are two different views of the image. So maybe one image, I can apply some grayscale to it. I get one view. And for the same image, I can apply some cropping, rotation, different views. So you're familiar with like all the self-supervised learning. They talk about different views. Essentially here, they were studying it in the context of, if I have a data, like if I have image, X1 and Y, image classification. Y is your task of image classification. What is a good set of views, V1 and V2? How should I design these views, V1 and V2? So that when I do contrastive learning on V1 and V2, it allows me to transfer to image classification from X1 to Y. Right? So it's slightly different notation, but the idea is the same. It's just in multimodal, you have X1, X2. Yeah. Yeah, of course. Of course. So, I mean, even before talking about this, you can use mutual information to measure shared information. Of course, it has its caveats. I mean, it's a nice formulation, it's a nice language to formalize things, but you're never really going to have P of X and Y and P of X, P of Y. But it's a whole related field of studying how to approximate mutual information, how to estimate mutual information for high-dimensional data, where you don't know what is P of X. Right. I mean, you got to keep in mind the fact that different data sets are created with different challenges in mind. Some data sets are designed to have 100% shared information. Image caption retrieval, or like VQA types of question, like tasks are like that. So you are exploiting the shared information, and that is almost maximal. Some data sets are created with a different goal in mind. So for example, when we talk about Fission, I'll talk about Fission in a little bit. You have lots of unique information, you have lots of emergence of information. So the shared information may not be that high. Typically, there isn't one number that you could hope to.
Like,
right.
Multimodal tasks, it depends more on that.
Right. Right. It depends on many. It depends on the task. Whether doing retrieval or captioning or something, or like Fission, it can depend on task. It also naturally depend on the modalities. It depends on how the modalities are collected. Right. So if you collect very precise images and descriptions, you get lots of shared information. You should be able to pair them up, compute a density ratios very easily. If you collect other types, I mean, medical sensors or self-driving car, it's not super clear whether the information is. So let me clarify. So you're saying X1, X2, two modalities are fixed, and just Y this might be different.
No, the modalities are.
Oh, Y is the same, but modalities are different. Right, yeah, then you expect it to be quite different. Because everything I was saying here doesn't really involve Y yet. I'll get it down a little bit. It's all saying just connections between X1 and X2, right? So yeah, so in the context of Y, different X1, X2 can be very, very different. So typically over here in the multi-view realm of things, when people have like one single modality but create two views out of it, they try their best to go into this case. So you're kind of making some assumptions, but you can kind of augment your views so that you're exactly overlapping by the amount of your task. Nothing more, nothing less. Of course, if you collect modalities, you don't necessarily have that assumption. Some may fall into here, some may fall into here, some may even be independent, and you still got to figure out ways of using them. All right, good questions. Very nice question. So that leads me to the next part, representation fission. Right? A lot of questions on whether these may hold, but in general, fission is a way of reasoning about what if this assumption of shared information being necessary and sufficient doesn't hold. So in general, learning different parts, different representations, representing different parts, not just in the shared part, but also in the unique parts, or if my modalities have many, many more clusters, how can I learn representations that represent each cluster? Again, a spectrum for more modality level fission, where if you have two modalities, you just have three representations, to more fine-grained fission, where you can go to even much, much more representations than three. But modality level fission is typically what we see the most. I'm going to assume that there is information in both modalities, but also naturally information primarily in language, not in vision. For example, different syntactic structure, different ways of using words to represent the same object, and information in visual modality that's not in text. For example, texture, depth, different perspectives, motion, they can't really describe easily in text. So that's modality level fission. We're going to try to not just operate in the space of learning the common information, but really see whether we can also learn information that is unique, that is not shared between modalities. And at this point, I also want to give a recap. We've talked different interactions that might exist between modalities. Right? Everything that we've seen so far on shared is probably in the redundant space, both modalities giving similar information. But when we talk about fission, we're also trying to learn all these other parts. For example, dominance is an example of information that is present in one that's not present in the other. And that information that is present in the one is important to the task. Okay? So again, we can look at fission through information theory. It's not going to be, I'm not going to cover all of this. It's still kind of work in progress, lots of open questions, but we're going to look at a very simple setting of how do we learn fission using information theory. So I'm going to assume there's four things we want to learn. Redundant information is the one that is shared by both modalities and the task. So for example, if I laugh and I say something funny, shared, both indicate happiness. Unique in modality 1 for the task and unique in modality 2 for the task. And finally, we're going to look at synergy. We're going to look at emergence, right? Can we actually quantify whether information can emerge, that it was not shared to begin with, that was not unique to begin with, but actually emerges when you combine them in the context of some task. And very quickly, you can see how classical information theory, the things that we've seen so far, might fail and that we need new extensions for it. So the classical information theory, like we saw these Venn diagrams previously, right? We saw X1, we saw X2, there's entropy in each one, that's the total area. There is some amount of information in the middle, that's the mutual information. And now I'm just adding a task Y, right? Because we're studying all of this in the context of some task Y. So I can extend mutual information to describe any of these areas. So one area we might want to be interested in is the information between X1, X2, and Y, right? What's overlapping between X1, X2, and also with Y. So that actually requires you to define a three-way mutual information. And the three-way mutual information is given by the two-way mutual information. So you recall X1, X2 is this area, right? The area of X1, X2 given Y is this area, but when you condition on Y, it doesn't contribute anymore. It's everything else that's remaining between X1 and X2 condition on Y after observing Y. So that's called a conditional mutual information. And it's actually a very nice, a very simple extension of mutual information to conditional mutual information. It's essentially saying what is the distance between two distributions, one of which is a joint distribution between X1, X2 given Y, joint distribution given Y, versus my product of individual X1 given Y times X2 given Y. Pretty natural extension, right? If you recall that in the case where we didn't condition on Y, the mutual information is just P of X1, X2 joint distribution compared to P of X1 times P of X2. How different those distributions are. None of this conditioning on Y, right? So same thing. So if X1, X2 are independent given Y, conditional independence, then this and this are equal, and my mutual information given Y is 0. Okay. A simple extension of mutual information to three variables. And over here, I can define maybe uniqueness as the mutual information between X1 and Y, conditional on X2. So I've already seen all there is in X2. I've conditioned on it in my distribution, the remaining X1 and Y distribution, how much mutual information there is. And likewise, I can also define unique in a second modality as conditioning on X1. I've seen X1, how much mutual information there is in X2 and Y. Okay. But there's some issues. First of all, this three-way mutual information, it seems like a very elegant extension, right? You have two variables, mutual information, and just take mutual information with a third variable. I get everything that is common to all three of them. It's nice, but it can be negative. So in fact, we never want mutual information to be negative, right? We always want it to be a positive amount of information. It tells me this much information. What does negative even mean? But essentially, because it's two differences between X1, X2 mutual information and X1, X2 given Y mutual information, if this second term is bigger than the first, it can be negative. So that kind of dumbfounded information theorists for a good amount of time. And the second issue is that there's no synergy, right? By definition, you cannot use mutual information to describe information that is not already present in your variables. So how do you quantify synergy? How do you quantify that two modalities combine to give you information not present in either of the modalities to begin with? So partial information decomposition is a very nice sub-branch of information theory that not many people may know about, but it's very interesting because it actually elegantly solves both of these issues. The negative issue, so it actually gives you a definition of R that is intuitive, yet is positive, doesn't have a negative issue, and it also gives you S, synergy, right? It allows you to quantify how much information is obtained from combining modalities that was not present in the individual modalities by themselves. So partial information decomposition, again, assumes that you have these four things, and these four things are what we care about, right? Redundant, shared to both and for the task, unique in each one, and synergistic. It's going to obey a couple of rules. It's going to obey the fact that the total information between X1 and Y, mutual information, is equal to the unique information in your first modality, plus the amount of redundant information shared in both. The total information between X2 and Y should be the unique information, plus the shared information in both. And the mutual information between X1 and Y given X2 should be equal to the unique information plus the synergistic information, right? Not redundant, because if I condition on X2, the amount of information that X1 additionally gives me is the synergy I get from X1. And likewise, if I condition on x1 and the additional information in x2 tells me about the label, that should be equal to u2 plus synergy s. Right. And in fact, you can show that under this new decomposition, R minus S is your three-way mutual information. So that essentially explains why your three-way mutual information can be negative. It explains it because if R is bigger than S, then it's positive. If S is bigger than R, your three-way mutual information will be negative. Okay. And finally, all these four things add up to be the total information between. Synergy is the information that is not in x1, x2 by themselves, but only obtained when you fuse them. The classic example is I say something very angry. I say something very positive, but I say it in an angry way, and together they indicate sarcasm. Right, so the sarcasm is not present in either one, but only when you combine them, you get information decomposition. The details are not necessarily the most important. I think the main takeaway is that if you want to understand fission, you have to understand different parts of information, right? Things that are shared, that's unique, that may be synergistic. And you can think of it intuitively using words. You can kind of look at this diagram, try to understand it intuitively. But of course, this is just a way of. And it's actually some very cool intuitions for what these terms actually end up meaning. So essentially, I'm going to look at all these distributions. So, look at, P. So P, x1, x2, y is my original distribution. That's my modality 1, modality 2, and the label. It's going to follow some pattern of mutual information. So x1, x2, and y are going to be they're going to have some mutual information between them. I'm going to consider the set of marginal matching distributions. I'm going to call them all other distributions Q over my modalities and label, where Q of x1 is equal to P of x1 and y, and Q of x2 and y is equal to P of x2 and y. So essentially, the marginals between x1 and y must be the same, and the marginals between x2 and y must be the same. So visually, that might look like this, right? It's going to consider all other distributions, where x1 and y overlap the same amount as my original distribution, and x2 and y overlap the same amount as my original distribution. The only difference is that my x1, x2 pairing may be smaller or maybe bigger. I'm going to consider all these other set of distributions. And then I'm going to define synergy first. Synergy can be defined as a total information between x1 and x2 for my task y. So I'm going to, over here, the notation means that I treat x1 and x2 as a joint random variable. I always concatenate them. And I'm going to take the total mutual information with respect to y. That's a total information both modalities give me about y in my original distribution P. Okay? Then I'm going to search over all the distributions in Q. We call Q are this list of all these other distributions. I'm going to search through all these distributions in Q, and I'm going to find the one that gives me the minimal amount of information between x1, x2 together and y. And you can actually show that this second part is equal to the total relevant information that has zero synergy. Why? Because if I eventually end up doing this optimization Q star, and I compute S again for Q star, it's going to be a total information that Q star tells me about Y, and another minimum. But again, this minimum is the one that I just computed, right? So this minimum over Q is going to again recover Q star. So I get I of Q star, total information, minus I of Q star, total information equals to 0. So by searching across the minimum across all of these distributions that has the least total information about the label, I'm essentially getting the multimodal distribution that has 0 synergy. So therefore, by minusing the total information I started with the total information in the distribution without synergy, I get the amount of. And since I defined all these different ways that R, U1, U2, and S relate with each other, you can then recover what R, U1, and U2 mean. Okay, and again, they're going to depend on some optimization equations. It looks very familiar with what traditional information theory gave me, right? I still have a three-way mutual information. You get x1, x2, and y to get R. I still have a conditional information between x1 and y given x2 to get u1, and likewise for u2. But the only difference is that I also must search over the set of distributions Q to find a one that either maximizes or minimizes these terms. And here's the intuition, right? How should I compute R? in order to compute R, I want to know how much information two modalities tell me about the label that is the same, right? Whether these two modalities tell me the same information about the label. I actually should be able to do that just by having X1 and Y data, how much X1 tells me about the label, and separately how much X2 tells me about the label. Using these two pieces of information, I should figure out how much information they tell me in common about the label, right? I actually don't need X1, X2 pairing information. That's why, again, this R intuition is that it only depends on things in Q, right? Because Q is a set of all other distributions where the X1 and Y is the same as P of X1 and Y. X2 and Y is the same as P of X2 and Y, but the X1, X2 might be different. Okay? So in other words, you don't need the pairing between X1 and X2 to tell you how much common information they tell you about Y and how much unique information they tell you about Y. Okay, I'm going to wrap up. But a very cool thing is that you can solve these actually very efficiently. Convex optimization problems, even easier than training neural networks. So you can actually take all these equations, plug into some solver, and get some really cool things, right? For things like sentiment, where you might express something positive and smile at the same time, there's lots of redundancy. You can actually run all these things, get all these estimates, and see there's lots of redundancy in these data sets, but also lots of unique information in language, right? Sometimes, language is our primary medium for communicating happiness and sadness, right? For things like sarcasm, you can run these estimators, again, very simple estimators in practice. You have lots of synergy. And that fits our intuition that when we are sarcastic, you express them through interactions between what we say and how we say it. But at the same time, there's still lots of information in language, right? Because sometimes you can be sarcastic just by saying things. And finally, as a sanity check for things like VQA, where the task is to purposely toggle between modalities, right? Where I can ask many different questions for the same image. I should get a different answer. That is almost all synergy, right? That is almost all emerging information because I can only get my label Y if I read both the image and the question. Okay. Any questions about these interactions? Ways of decomposing your total information into these different parts. X2 and Y is all the way over here. The Y is not connected to X1, X2. Well, then the total information is going to be 0 for everything. Right. But it'd be cool to analyze in your case is multi-hop in the sense that you have X1, X2, you have like a Y1, and you have Y2, Y3, Y4, Y5 until you get a final answer. So the Ys are changing, right? But how can they evolve across time? So that, yeah, it'd be interesting. All right, so that was the intuition between shared and unique. We also talked a little bit about in the context of why. But how do you actually learn these things in practice? So one popular way of doing it is to learn factorized autoencoders. So I can start with two modalities. I can put them through two representations. One representation that is meant to have the common information, must take in both. And the two representations that are meant to learn primarily unique information just depends on each one. So many times we assume that the common information is used to predict the label. So if the label is in the common space, at the same time, you're going to assume that these unique representations are going to help you regenerate your data. Right. So the common information is used to predict the label. There's some discriminative loss over there. And together, the common information and the unique information can help you together reconstruct your data, right? So essentially training this in an autoencoder manner, where there is some discriminative loss to predict the label, and also generative loss to reconstruct the modalities. And finally, there's a loss that says all these three factors should not overlap with each other, because what is shared should be independent and not overlap with what is unique. So you can do that using putting priors that enforce independence on these two representations. That was back in the autoencoder regime, but essentially here what you're doing is that you're basically learning, reconstructing the entire data. Another recent way of doing it is to just do it in the context of your task Y. So I can learn three representations, one that captures the mutual information between my two modalities and the representation and the task Y, one that learns unique information, so just how my first modality contributes to Y condition on the second, and one that learns how the second modality contributes to Y, independent condition on the first. And the idea is, again, the result, the method is quite simple. So if everything in the mutual information is learned through contrastive learning between images and text, then how you can learn information as unique in the first modality will be self-contrastive learning. So taking in data from the first modality, applying some augmentations, and doing contrastive learning there to learn representations. And again, for the second modality, taking your data, applying some augmentations, and doing contrastive learning there. So it's a simple way of getting representations that both capture the shared part, so that's contrastive learning across the two modalities, and also representations that learn the unique parts. So contrastive learning within modalities. Okay, any final questions about fission at the modality level? Shared unique information, yes. I think it's solving quite different challenges. In this clustering, the goal is to cluster your data, typically in an unsupervised manner. And as you mentioned, you have to set a number of clusters. Here it's more to learn representations for some downstream tasks. Of course, when you end up doing self-contrastive learning, you're going to end up with clusters of data. Because essentially what we're doing here is that if you have an image and you do an augmentation, you want them to be similar to all the augmentations, and it should be different from other images and other augmentations. So it is still doing some kind of clustering. It just may not be the type of clustering you typically expect from k-means clustering, because over there, you want your image to be clustered with other similar images. Right? So, okay, so over there you have text. And you're right in saying that multi-head attention, they learn different subspaces of features in text. One might learn part of speech, one might learn language, one might learn tense, and so on. So it is still kind of discovering clusters in your data. So in fact, that goes more with the fine-grained fission I was going to talk about. But yeah, you can think of it as having a relationship. Of course, whether you actually do it for like a vision language transformer, and it actually ends up learning some parts, which is language only factors, image only factors, and some common factors. I mean, it'd be good to see whether that actually holds in vision language transformers too. Okay. And just one last 5 minutes on this fine-grained fission. It is not commonly seen that much, but modality level fission only looks at it at the modality level, shared, unique, and so on. Fine-grained fission can go much more fine-grained to actually discovering individual clusters in your data. And well, thank you to the student for mentioning clustering. A lot of works in fine-grained fission are going to do clustering in some representation space. So here's an example of multimodal clustering, where you have images through some image encoder, audio through some audio encoder, learning a space from both vision representations and audio representations, and clustering within this space so that you actually get aligned representations at the cluster level. So aligned representations for baby, video, and sounds of babies crying, aligned representations of drumming and sounds of drumming, of background and sounds of background. And so essentially you're combining what you've seen kind of previously with the fact that you are still learning coordinated representations of both shared and unique information, except now you do further clustering so that you're not limited to 3 representations, but you can get representations 1 for each concept, or however many clusters you choose. All right, I'm going to wrap up. So we've seen representation, a big topic in multimodal, perhaps the challenge you're going to see in any multimodal task. Looked at fusion, coordination, and fission. Fusion is all about combining elements from modalities into one representation, taking into account the different ways they interact with each other. Coordination is about learning 2 separate representations. A lot of study there is how you define that similarity function. And given that similarity function, we showed that all these contrastive methods essentially recover the mutual information, right? It maximizes the lower bound on the mutual information between modalities. If you think just capturing the mutual information, the shared mutual information between modalities is not enough, you can then go to fission, where you can try to understand what is both shared, unique, or different clusters within your data. So some of the key slides that we talked about is that things like clip capture the mutual information between your modalities. It's going to discard the unique information. And this is good if your task relevant information lies exactly in the shared parts. If you don't, you can then go to Fission, where you learn both what is shared and also what is unique across your modalities. All right. Thanks, everyone.